All right, hello world. I am back. This might be a short one today. Just doing like partial fraction decomposition stuff. I think it's frustrating me is that this is definitely tearing the book apart, me holding it like that. Anyway, um, we had done 23. I've gone over it like 3 times now. um, 24 I looked at once in the previous video last week. If you can see this, it's sort of the usual thing, right? So here you'd have the product of the two geometric series, 1 over 1 minus zeta, 1 over 1 minus zeta to the fourth. But instead of looking at the nth coefficient, you're looking at this strange number. It's an odd n minus a square, odd n minus a square, odd n minus a square. And it matches up with that square. So I'm just going to kind of wave my hands on this one because I did talk about it last week. I was able to get this down. And I think I trailed off there. Yeah, I think I didn't explain this part in the middle. He's doing that telescoping trick again. But I was going to have to look at this again. Yeah, and then I was reading this comment. So we did look at 24 before, but like I didn't make a lot of headway on it. And I don't want to get stuck in the weeds right at the outset here. So we're going to move on to 25. I'll see what I can do with it. I have seen it before, but yeah, it's kind of a straightforward one. So the question says, take this equation, x plus 2y plus 3z equals n. And the number of solutions to that, native natural number solutions to that, including 0, I suppose, including zeros. Anyway, the number of solutions to this is the integer closest to this quantity, and it's, if you can read that, but it says n plus 3 squared over 12. So I'm looking at 25, and that's the one I want to get down today. That one shouldn't be too painful. We have one equation is equal to n, right? What is different about this? I guess one thing that's different, all these previous examples we had been doing, except for 21, they were only two terms on the left-hand side of the equation. Two terms, two terms, two terms, right? There's a bunch of them, so you sum them all up, but it's only two terms. This one, there's a third term there. Anyway, the typical way you approach this is to say, if I look at this series, if these other terms weren't there, the coefficients of this power series would give you the number of solutions. I realize that's kind of silly because it's just a 1, and there would just be a 1 in each case, but yeah, we take a product like this, and now if you were to expand this, again, the nth coefficient in your expansion is the number of solutions to this equation. Just pausing for a moment. I wanted to say it doesn't take order into account. It's more like the making change type of problem. Yeah, so 21 is actually, sorry, this 21 example is actually a little bit different because this one the order does matter. It's a similar approach, but you don't just start from, right. It's like, it's a similar approach. It still involves geometric series and such, but it's actually subtly different. It's like, if you want to use 4 terms, you take your stuff raised to the 4th. And if you want to include, so if you want to include 1, you have a zeta. If you want to include 2 as an option, as a term, you do plus zeta squared. If you want to include 3, you do plus zeta cubed. You put that stuff in parentheses, and then whatever power you raise it to is the number of terms that you've got. Anyway, just kind of lightly reviewing here. We talked about that in the past. But for this one, this would be the approach. You know, the idea, if you're wondering where this is coming from, we've talked about this for a couple weeks now, but the idea is that right, this is what the geometric series looks like. And then we've even got a cube one here. Oh, you're going to be running out of space here. Right? And when you multiply these, it's not so much the order matters, notice. You just get the coefficient. So like if I take zeta to the 4 times zeta squared, the overall sum is 6, but it comes from 2 terms like this and 1 term, or sorry, I guess 2 terms like this. So it would be, that would be the solution 2x plus 2 times 2. Like you let x and y be 2 in that case, if I grab that particular pair. You get a sum of 6 in the exponent. So you can see why I'm saying like the order actually doesn't matter here. This is closer to the very first problem of the book, where he says, how many ways can you make change? And then he starts talking about solving this equation. So that's why I'm comfortable with this approach, because we talked about it back on number 2. Yeah, I need to come up with a better way to hold this book open. I'm starting to get nervous about the spine. It's like just glued. And it's not a cheap book. But anyway. So I'm looking at 25. I think I just want to approach, I think we just want to do 25 today. That might be plenty for one day. We were trying to find the number of solutions of this. This one equation. So I'm saying if you were to expand this and, I don't know, call the coefficients an or something, then the solution is an. An is the number of non-zero integral solutions to our equation. So what? What are we going to do with that? What he does is a partial fraction decomposition on this stuff. Starting to think, like, how does that actually get me? You can do that, of course, but will you then have zeta to the n? For one thing, before I come back to this, we should like review partial fraction decomposition, right? If you had something like, let's say, here's kind of an easy one, right? Because this is reducible. It splits over the rationals like this. So anyway, the concept, of course, from Calc 2, I'm sure you're familiar with, is if you've got distinct, especially this time we have just linear, they're single powers upstairs. This is probably the simplest case. I don't know if I'm going to do the whole thing out, but you can evidently write this as this sum. And then you do some fiddling, you do some algebra, you find out what these numbers A, B, and C are. By fiddling, what I mean is you usually multiply by this denominator on both sides, so you get 1 equals, and then you got a product over here, like some stuff cancels. So this is the same as saying 1 equals, and then if I were to distribute, if I were to multiply this denominator on both sides, well, this x is going to cancel, but you're left with these two factors next to the a. So I get a times the x squared minus 1 term plus b times, and then this guy cancels, but you're still left with these two factors by the b. And then x plus 1 cancels, and you're left with these two factors times the c. I don't know what we want to call this, but it's an identity that's true regardless of what x you plug in, including x's that don't make sense in this original fraction. So like I tend to do that to get the answers. Like if I plug in x equals 0, well, that's going to kill off these two terms, but I'll have a number here and I'll have basically solved for a. So we can finish this problem. The rest of this is just kind of arithmetic. If x were 0, then you'd get in a statement like 1 is a times negative 1. And if x were, say, 1, then both of these terms are going to cancel, but you'll still have a term in the middle. So if x was 1, say, you'd get 1 equals b times, let's see, 1 times 2, so 2b. And finally, if x is negative 1, these two cancel, but this guy does not. You get a statement like 1 is negative times negative 2, so I guess it's 2c. Negative 1 times negative 2 times c, so it looks like positive 2c. Anyway, so the a value up here was negative 1, the b value is half, the c value is also half. And we could verify that, but I'm sure it's fine. Another thing we're going to want to look at, I think, is like the complex case, because like I already know he has, as part of his answer, he does something like this. He factors that, okay? Which, unfortunately, I mean, I know you can factor a single x out like that, but then you're left with, I mean, my instinct would be something like this. Does that make sense? This minus x times itself. You would get x and x squared would be gone, but you'd still have an x cubed. Yeah, that's right. This denominator factors like this, but then you're stuck with this thing, which is irreducible. So let me just play with this for a second. Generally, what you do with the irreducible stuff is, like, if it was over the reals, you would have to leave it like this, and then you could still solve for b and c. The work is a little more complicated, but, you know, we still do the same trick. We multiply this denominator on both sides, and we get stuff like 1 is a times this, and then this cancels there to give you just the 1 minus x part. So bx plus c times 1 minus x. Okay, so this is the kind of thing I can plug numbers in. If I plug in x equals 1, we get an answer for a, like 3a equals 1. But how am I gonna, I don't have a root for this, right? I would have to plug in a complex number. So another thing you could do is group these terms, like actually distribute this out and see what you get. I don't know if I'm really going to enjoy that, but let's see what happens, because then we'll get a system of equations that I can solve, you know? So yeah, let's go ahead and do it. This is a plus ax squared. And then when you distribute this, you get bx plus c. You also get negative bx squared minus xc, minus cx, like that. Yeah, so what? So the constant is 1. And then over here you have like 0x and 0x squared. You're just going to be equating all those coefficients. On the right-hand side, the constant term is this. Oh, that's not constant. Here's a c. That's constant. But the rest of them have x's in them. So the only constant on the right is a plus c, it looks like. So I now know that a plus c is 1. And there's more stuff here. Ax, bx, minus cx. So if you take a plus b minus c times x, those are the x terms on the right-hand side. And there's a couple x squareds here too. We got a minus b. So I know that this is 0. Oh, that's cool. That means a is b. We already found a, didn't we? And we also know that this is 0. So we're pretty much, you know, it didn't turn out to be as bad as I thought it was going to be. This is a small example, of course, just this example up here. But I'm doing partial fraction decomposition. I'm over the reals, because if you were over the complex numbers, this does factor. Everything factors, but you'll get different answers than what I'm doing here. So I'm just giving you an example. In fact, this is a little distracting because that's not how we're going to do it. I think, I mean, all of his answers are real in the answer to the one we're looking at, but he's clearly factoring it over complex numbers. So I'll do that example in a moment. But the rest of this story is just, we know that a is a third because I plugged in 1 into this identity, and it kills off this term, and you're left with 3a equals 1. So that's how I got a. And now I know c as well, right? If c must be 2/3, because this is 1. This is the constant term, and we said it's equal to 1 on the left. So if that happens, I guess that means c is 2/3, so that the sum of the two is 1. And we also know b, because b is the negative of a. If I add them, well, not add them, but like a equals b. Oh, yeah, I misspoke. They don't add to be 0. They differ to be 0. Anyway, b is equal to a, but we already know a is a third, so b is a third. So the final story here is that this guy does factor. It can be written as a difference of two fractions, but it's a little gory upstairs in the numerator. You know, we get 1/3, 1 minus x, and then the b is also 1/3, and the c is 2/3. And then downstairs you get this irreducible junk, 1 plus x squared. So that's how you would do it over the reals, right? And I'll see if I can figure out what the heck I'm doing over the complex numbers, okay? I'm just winging this. It's been a long time since I mean, honestly, it's been a long time since I even did this, but you don't really forget that stuff. But for complex, I don't know. We only did it a handful of times. I don't know if I ever really did it. So let's look at the same example, but I'm going to try to factor it over the complex numbers this time. Pretty certain. Well, I mean, if you let the numbers be complex, all right, before I even jot this down, what I should do is try to factor this guy. Like, this is x minus 1 times, I want to say, did I screw this up already? No, that's right. That's right. Stuff in the middle cancels. So factors like that. Now, what I would usually do to factor this over the complex numbers, right? There's one obvious observation is that, like, if you have something like this, you sort of need to know this. This factors over the complex numbers. It's x minus I, x plus I. You got to know that or else nothing makes sense, you know? So this is x squared minus I squared. Or, you know, x squared plus 1, x squared minus negative 1. So if you believe that I squared is negative 1, then this is true. And therefore, everything's going to be factorable, including this little mess. So what you would do is complete the square on this, is the way I've been doing it. Right? If you expand this, it agrees in the first two terms, of course. But then you get a plus 1/4, which is not what we have. So we're going to need to correct that by doing that. And so I really should have done a more general form of this. What if we had like plus a squared here? Would it be, is it minus IA plus IA? So that you get negative I squared a squared? Does that make sense? So that's a more general form for factoring, right? I'm going to need that right here because this is not a 1. So you can factor this. We're going to treat it just like this. Here we have, I don't know, capital X is this little x plus half. You know, we're basically looking at exactly this formula, but with these slightly less pleasant numbers. Yeah, so anyway, it factors. This is x squared plus, you know, a squared. We're claiming it's x minus ia, x plus ia. So for our mess, it's, you know, x plus half minus I times, not 3/4, but the square root of that. Is it okay if I write root 3 over 2? And then over here we'll have x plus half plus I times the square root of this number, root 3 over 2. Ugh. But it is what it is, I suppose. So that's why I paused up here, because B and C, since we're factoring over complex numbers, B and C can be complex. They might be complex valued. But downstairs, I'm kind of expecting, maybe it's the other way around, right? It's like, it's the negation of these two things. That doesn't actually matter, I suppose, because the negative will just get absorbed into this numerator. But anyway, these are the two terms that are going to go down here in the denominators, right? That's how I factored this previously irreducible junk. It didn't split over the real numbers, but it does split into this mess over complex numbers. So that's basically what I'm putting up here. I started to like wave my hands about the order, but no, you can just put exactly these. Don't worry about the order. It's not actually the negation. I don't know what I was thinking. It's actually this term. You know, this factor is like this. If you go the other way, if you negate it, then you're just going to negate this, which I already did. We took care of that. So this junk is the you know, factors into these two terms. These two terms right here and right here. So plop this guy over there and plop this guy over here. Oh my goodness. There's probably a smarter way to do this. Like, I'm just not super, you know, I haven't caught up on it. Like, you can let omega be some sort of root of unity, and express this as like x minus, what is it? It's going to be, I don't know. I'm trailing off here, losing my train of thought. But I'm sure there's a simpler way to express these. You know, something like 1 minus omega x, 1 minus omega squared x. Maybe if I keep going with that, it'll work. Hey, thank you for the follow, Zone Ranger. 1. Ugh. I mean, I'll get some stuff in the middle that is x, and we can see that the coefficient is 1. Yeah, sorry, I'm trailing off here. You can see I've suddenly become out of my comfort zone. And of course, omega cubed is going to be 1. So omega squared is something new. It's 4 pi over 3. But omega cubed is going to be 1 in this expansion here. I'm just thinking out loud if there's a way to... did I do it? It's not this, right? It's not something like that. What if it was? All right, so you'd get, in the middle, you'd get w plus w squared, and then of course you just get the 1, minus 1, I guess, which doesn't quite add up. Oh, is it IW maybe? Maybe that's what I'm thinking of. So that way this becomes a plus. But in the middle, is it? Minus IW minus, so that's fine, it just puts an I here. And so then if I was trying to factor this junk, my new identity is, anyway, I realize it looks like I'm being crazy here. It relates to the answer to this problem. That's why I've gone off on this tangent. Believe me, it's worth knowing how to do partial fraction decomposition to solve the problem we were talking about. I'll reiterate what the problem was in a moment. But this is going to end up being basically all of it, is can you decompose a product of stuff that looks kind of like that? And then we had a +1. That part's fine, but in the middle, I guess I'm saying, what are you doing here? Didn't mean to do that. I wanted to write x squared plus x plus 1. So I guess this stuff is 1? Yeah, of course, but like, so what? If I divide by this, you will get I. So I guess you're getting this equals I, right? Yeah. Is that true? It could be true. It feels right. 2/3 pi is over here. 4/3 pi is down here, of course. I don't think I'm getting I, man. I think I'm getting a real. So I guess that tells me no, why wouldn't this have worked? You can't just be wrong about this factorization. There's nothing wrong with writing it this way. It's just that this is not omega. This was my guess back when I was trying to write it like this. Yes, indeed. What does that one do? So this was like 1 minus... this is probably wrong. Feels weird to me, but we'll do it anyway. We'll do it out. Maybe it's this. Here I am, like, poking around. You'd think I would review this before I made a video about it. But yeah, omega plus omega square x, and then the last term is the negatives cancel. You get plus omega cubed, which I'm claiming if we use this, I think it's connected to this factorization. You'll get a 1, so you finally get plus x squared. So this time, if I'm right about this, that's how I got omega cubed. Oh no, I used it here too, didn't I? I did, didn't I? Right here I assumed that omega cubed was 1. Alright, we're going to have some problems there probably. I don't know. But the sum of this is definitely not I. It's a real number. You could even like, well, whatever. I'm all over the place. Let's see. So plus omega cubed I'm claiming is 1, and then x squared is squared, and then this stuff in the middle we would like to be 1 because it matches this part. That's what I'm trying to factor. Hey, this time that's correct. That's what I expected to see when you add omega and omega squared. Just to prove it to myself, here's omega, and here's omega squared. Like this times itself, you would add the exponents, of course. You know, and I'm claiming that this is -1. I'm probably freaking wrong. But it's an easy one to check, right? So cos 2 pi over 3 plus I sine 2 pi over 3. And then to that we're adding cos 4 pi over 3, I sine 4 pi over 3. Curse you, feeble brain. I don't know why you're thinking so hard about this. The signs cancel, right? Sine of 2 pi over 3 is like, stupid pre-calculus that I don't remember. It's the smaller of the two, right? So it's going to be 1/2 comma √3 over 2 is the reference angle. So yeah, anyway, this is positive √3 over 2, but this one is like, it's sort of like the negative angle. It's going to give you, down here, it's going to give you negative √3. So these cancel, and you're getting a real number. That's why I kept insisting that. But the number that you get is -1/2 plus negative half. Okay, so it did work. This works out to be negative 1, like I thought. Yep. Why am I so excited about that? Because this is true, which means this is the correct factorization using this omega. This is the same as x squared plus x plus 1. So great, who cares? Well, I didn't want to write it like this, okay? This past 5 minutes of me rambling is I didn't really like this. You see, it's the same thing I just wrote down. It's this number, x plus omega. It's omega. It's 1/2 plus I sine. But I don't know. I wanted to know what omega was, and it's clearly this. So I'm okay. So I think that's x plus. It's like x plus or minus omega, right? Is it just this? For some reason I did this is what I verified it was equal to. It feels more correct to me. Does this work too? Why would this work? It might work, I guess. Anyway, I'm off on a tangent. We'll get back to the real question in a minute when I finish doing basic algebra. Wx minus, what are you doing? What are you doing with that? Don't do that. You meant this, I guess, but now I've got lots of question marks. Do you think it's also going to factor this way? Why would it do that? Sure, give it a shot. Why not? Who knows, man? And the last one is w cubed, which is 1. So we can just write it like that. And in the middle, we get this statement. Evidently, this equals 1. But we just showed that that's not actually true. So this is wrong. This is not true. Because we're supposed to get negative 1 in the middle, not this. So, yeah, interestingly enough, if you wanted to put a negative sign, no, because that messes this up. Yeah. Alright, so this is just not the way to factor it. But this worked. So why am I saying this? Well, I was trying to factor this term over the complex numbers, because over the reals you have a linear thing up top, like bx plus c. I don't want to do that. I want to have just numbers. Anyway, you can factor this over the complex numbers, and I was trying to figure out a nice way to write this denominator. So of course one of the terms is 1 minus x, but then you're left with this stuff. And that's what I was trying to factor, completely split it over the complex numbers. And apparently it factors like this: 1 minus omega x, 1 minus omega squared x, where omega is the cubed root of unity, e to the I 2 pi thirds, like that. Okay, if you use that as omega, this is how your partial fraction decomposition is going to work. You still got to do the rest of the work where you multiply with the denominator, you find a, b, and c, but this time a, b, and c are complex numbers, of course. So if you distribute this, should we finish it up just because, almost finished with this page, may as well see what it does. But distribute this gives me 1 equals a times, and then we have, you could write both of these if you want, or you could just distribute it and get this mess, x squared plus, I'm going to go ahead and write it as the original form. But yeah, this times this term, the 1 minus omega cancels, and so you have the other two factors, of course, right? Isn't this like much more pleasant? It's really not bad. And then this one cancels, and you're left with the other two. 1 minus x, 1 minus omega x times c. And it's okay to plug in like if you plug in omega, say, for x, you'll get a 1 here, and so this one dies. Here it doesn't quite cancel, but here it should, right? I think we've established that omega squared plus omega equals negative 1. So if you plug in omega, it'd be very clear if I wrote down the two factors, right? So you can plug in stuff, the same trick as before. You can do like, if x is 1, then these cancel, and I get 3a. If x is 1, it looks like I get a equals a third. And if x is omega, this dies, and you're left with this mess. 1 minus omega times 1 minus omega squared. Which I don't know off the top of my head. That's this when you plug in x equal 1, right? So it's got to be 3. It's got to be 3c, like c is a third again. That's confusing. I mean, okay, it happened. And then for the middle one, you just plug in negative omega. This will survive. It looks like it's going to be 2, although you have a complex number here for x, okay? So it looks like b is going to be complex. That's confusing, but I guess it is what it is. The negative omega over here gives you 1. Oh no, it doesn't cancel. Huh. For some reason I thought it was going to cancel on me. So maybe b is... Alright. I'm losing it. Before I just throw this all out, let's actually just... It doesn't look that bad. Let x be 1, you get 3a, these are 0. You get 3a is 1. That's how I got that. If you let x be omega, this dies. And for some reason I thought this also, but maybe I did it way too fast. No, I'm right. Omega cubed is 1. You get 1 minus 1. So this is not wrong. X being omega should kill off both of these terms, because it has... Right, it has this as a factor. That's why it's canceling. So naturally it's leaving the only thing that had as a factor. So yeah, if you plug in omega to this, these are gone, but maybe I made a mistake. Yeah. That's I knew that something was fishy with that. I was like, that's weird. How do we get a real number? Yeah. If you plug in omega, you're getting 1 equals, these are gone, and then this is 1 minus omega squared. So that's, okay, I see. For some reason I thought this was like, oh, yes, indeed. Why did you think that, Dave? Because it simplifies to be 3. I can see it now. So I guess it is fine. Huh. We sort of already established that this product would give you back this. Indeed, we did. So, okay. So if you let x be 1 up here, you'll get this statement. We get 3. We get 1 plus 1 plus 1. So, 3 c's. So, c is indeed a third. Don't panic. Alright, so the one that sucks is when you plug in negative omega, because it doesn't all cancel quite cleanly. The first one does. This one should have. So I'm going to take a look at that again. Oh, omega, you don't want to do this. I want to do omega squared. That's what's going to make this cancel. And this cancel. Wait a minute. Doesn't it become a 1? If you plug in omega squared, you get omega plus omega squared plus 1. Which is 0. It is 0. Okay, good. Sorry, I was plugging in negative omega. It's an inverse of sorts, but it's a multiplicative inverse, not an additive inverse. You don't want to do this one. That's not going to help us. I mean, it was fine. It'll give you something, but this will be a little easier to work with. So let's do that one. If I let omega squared, if I plug it in here, I'm claiming here you get 0. Here you don't. You get something else. Oh, you know what we get? This better not be third again. I think it is a third again, right? Because this is the same equation. I'll write it down in a minute. But here it cancels. Omega squared in here at x equal omega squared, you get 1 minus omega squared times, well, here it is, 1 minus omega cubed, but omega cubed is 1. So that's gone. And what you're getting is, of course, 1 minus omega squared times 1 minus this guy, omega squared times omega squared, which is a lot like just regular omega. We can write it as 4 if you want, but we're getting this statement now. But this is omega. It's like mod 3 because it's a cubed root of unity. This is 1 times omega. So again, we're just getting this guy, which I believe we said was 3. At the beginning, we had established that this whole thing has been factoring this into 1 minus omega x, 1 minus omega squared x. So you can factor it like this. And that's, again, what we're looking at. You just let x be 1, and you'll get this product. So if x is 1, we get 3, which means this says 1 equals 3b. So after all that work, it just tells me that b is also a third. A and b and c are a third. So like the way that you factored this, you can factor it like this. You can put a 1 minus z, and then you're left with z squared plus z plus 1, right? But we said that factors, where is it? This factors like that. So these other two terms look like this. Again, this is where omega is the root of unity, e to the I 2 pi over 3. So yeah, I put an a, b, c here. Apparently they're all 1/3, if you believe it. I guess I'm going to try to check that now. So we have a common denominator of this, of course. This one's missing these two terms. Or you know what, let's put a 3 over here and see if it works. So like, we're claiming that this happens, distribute the 3, multiply the 3 out, and you'll get 3 over this stuff equals the sum. So let's see what happens when you take that sum. It might be like a little easier said than done because this is some complex number, but yeah, so when you add these fractions, this guy's missing these two terms, whose numerator is, I suppose, z squared plus z plus 1. And then this one's missing these two terms. Sadly, I can't do a cute trick like I did with this one. It's that. And then the last one is missing the first two terms, which is 1 minus z, 1 minus a single omega z, all this stuff over the common denominator. All this stuff is times, divided by the common denominator, 1 minus z cubed. And we want to see if this stuff works out to be 3. The point is that all this junk is apparently 3. I didn't really see that coming, but this is an easy example. Maybe it's supposed to be 3. So we get some gory algebra over here, right? 1 minus z minus omega squared z. All right, let's just do it all out and then group the terms. 1 minus z minus omega squared z, and then plus omega squared z squared. That's what's in the middle. And then over here I also have 1 minus z minus omega z. Look at that, 3 1s already. It's working, man, it's working. It's going to be 3, just like we thought. So I think this is correct. I think the factorization worked. But we'll finish it. 1 minus z minus omega z. And then the last one is plus, you got plus, right? Okay, good. Plus wz squared. Plus omega z squared. So it's a 3, but does the rest of the stuff work out to be 0? Is that true? It doesn't seem true. Oh, I do. Okay, so there's a z there as well. I swear I'm getting minus z. We got 1, 1, 1. That's the 3. looks like z minus another z. So that sucks. Oh, I missed this one. And this one. Okay. Alright, so I grouped some of them, but then there's also... Yeah. That's why it's going to add to 1. I see. It's going to be 0. But here, let's do it. We got minus z. We also have an omega z over there, and we got an omega squared z here. And notice what's happening is this is z, yeah, but it's times 1 plus omega squared for this omega, which you can actually show that that's going to be 0. In the complex plane, you're looking at these 3 numbers. It's like an exercise in complex variables to show that this sum is equal to 0. If you took like k over n, you let k go from 0 to n minus 1. Anyway, you get a shape like this. These are going to cancel. Or you could just probably plug it into our original. Like, isn't this just this equation? If I plug in omega for x, we get 1 minus 1, like right there. If you plug in omega for x, you can see, based on our factorization, that this term is 0. So there's a couple reasons this is 0. But we're getting 3 minus a thing that's equal to 0. And then for the z squareds, I bet the same thing happens. We got z squared times 1 plus omega from this one and plus another omega squared. So the same thing happened for that one. So it is 3. 3 minus 0. So okay, so I didn't screw up the factorization. I'm not going crazy. That was partial fraction decomposition over complex numbers. And that was a long aside. Why did we do all that? Back to the story. Okay, see that guy? He's part of our answer. See that little mess right there? Now, so the original question was, how many solutions are there to this? X plus 2y plus 3z equals n. So for a fixed n, how many solutions are there? When I say solutions, I mean non-negative integer solutions for x, y, and z. Okay, that was the original question. That was the whole point of today's conversation. Is I'm looking at number 25 in the book, and it's a neat one. I'm gonna see how far I can get answering it, and then I'll look at the solution in the back. But it's really important because he generalizes it in 27. Like for 25, he just says this pretty straightforward example: x plus 2y plus 3z equals n, and he says the solution is like the integer that is closest to this number, n plus 3 squared. N plus 3 squared over 12 is apparently the answer for that, which we're going to see in a sec. But the reason I'm the reason I'm focusing so much on number 25 is that 27, he says, all right, give yourself L positive integers that don't have basically relatively prime integers. Okay, they don't have a common factor other than 1. And then look at the number of solutions to, and this is the equation that he gives you. So it's the same equation, he's just generalizing 25. Instead of, 1 plus 2 plus 3, he's got L variables there. And then the solution is that, for this part, he says, okay, well, notice that your number of solutions, if you divide by, n to the L minus 1, it'll cancel out, and you'll get this coefficient. And so his answer is like a one-liner. It's really easy if you know the decomposition thing. Basically that kind of answer is going to pop up in this as well. So I really need to get 25 down to understand 27. But then we're finally done with these types of questions. He's done a bunch of these. We did 3 of them in a row. 22, 23, 24 are all variations. 22 is a little easier. 22 is the base case. And we've been doing stuff like this. Back on the first page, we did this one as an example. So anyway, but luckily, look at this, we are finally moving on. Once we get to the 30s, we move on to binomial coefficients, and we don't have to deal with these things anymore. Although there's still a few more gory questions, like how many lattice points are there in this octant, or whatever, this octahedron space, or like how many lattice points are on this cube that satisfy that are between two values. I guess the plane lies between two fixed heights or something. Anyway, we're gonna have to get to those ones another day. But today I was trying to just get 25 down and get it down like real well, because the answer for 27 is just a generalization of this type of question. So if you can do the partial fraction decomposition BS that makes this work, you can understand 27. And then I can finally move on. So before if I were to answer something like this, I would say, okay, what we've been doing is you take this geometric series times this geometric series times this geometric series, and when the coefficients sort of interact, when you multiply them, the exponent is the sum on the right-hand side. So like these terms represent this term. Like these terms in your factor, like this factor represents various values of x, or like that term. These ones represent various values of y, like this is y being 1, y being 2, etc. This is z being 1, z being 2, etc. The 1 is there just to capture, z equals 0. So if we want to get all non-negative integral solutions to this, what you should look at is what's called a generating function. It's this form. It's just a power series, but the coefficients of which would give you the number of solutions. This is that series, and that's kind of what he talks about back on number 2. So that's why I'm so comfortable saying, like, oh, you want to find this? Well, you should look at this function, because if you were to expand that, the coefficients is your answer. The nth coefficient would be what you're looking for here. Would be your answer. Here, I jotted it down over here in my little scribble. An is the number of solutions to this equation. So yeah, but that sucks, right? Like, how am I supposed to expand this? Well, you can do a partial fraction decomposition on this mess, is apparently what he does. And maybe I should just spoil it for you. Where is it? We were doing 25. Yeah. Because I've already seen this, that's why I'm like trying to get it down so well. There's his omega, that's that cube root of unity again that I've been talking about. So those two terms are how he factored that guy, One of the terms is 1 minus zeta. That is there also. But the other two terms are this zeta squared plus zeta plus 1. How am I going to factor that? Well, you're going to have to split it over the complex numbers. And that also explains this junk, this cosine business. But we'll get there in a second. So yeah, that's, believe it or not, this is his answer. It's really not that bad. Looks like it's due to Hardy. I'm not familiar with Waring's problem, but this book, by the way, was written in 1928. So all these references are prior to that. That's why this is like a book. This is like a paper from 1920. Oh yeah, change problem number 9. Okay, no, he's just saying in this book he calls it the change problem. This tactic where you take a product of of various geometric series to try and solve something. So he calls it the change problem. Also, number 9, he did a generalization of like all of them. But anyway, yada yada yada. Here is your answer. To continue, you're going to need to write a partial fraction decomposition. So that's why I spent the last 45 minutes reviewing partial fractions. So this one splits. That's no problem. You get, where is it? You get these two. And of course this guy's linear, so you just get that one. But this one splits into that times those two. So now I'm like a little confused why these two are there. Right? I wouldn't have written these two at all. I would have just written this guy and those two, because I think that this product gives you that. But this is there. Is he ignoring them? I don't think so. Yeah, they're there. He's claiming this equals that, which I'll totally buy. I'm gonna do that. I'm gonna do the workout, but like, why am I so confused? Oh, I'm an idiot. I see. Because there's 3 of these, of course. Good, 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 good. Yep. All right. It all makes sense. It's good. Because there's 3 of them. There's a factor. Here's a factor. 1 minus zeta times 1 plus zeta. So there's your square factor. And then here's another factor. 1 minus zeta times the 2 weird guys, the complex guys. So of course there's 3 powers of 1 minus zeta. That's why it's cubed. So you do need to include that. Okay. I'm sorry. Got distracted there for a minute. I was like, why is that there? All right. So yeah, this one is not as insane as you might think, but you got to know your partial fraction decomposition or you get stuck immediately. I like never know what to do after this. I jot down the first part and then I'm like, okay, that's a power series, but how do I get it? Like, how do I get the actual coefficient? And that's, unfortunately, it kind of depends on the problem. For many of these, he's just been like, well, it depends on how bad it is. Some of the questions he has multiple, like if he has multiple questions, like if he has multiple equations that he's trying to solve, he'll just add them, of course. He'll take this plus this plus this. And so you get a series and you really kind of fidget with the series. You try to make it like a telescoping thing. But my last 3 videos have been about that. The last 3 VODs that I put up on Twitch have been going over those examples. And then the earlier examples, I mean, I guess it's really just the same thing. He's just kind of fidgeting with geometric series and it pops out. This one is finally like, I guess we're going to do a partial fraction decomposition for some reason. Let me change this to z. So this is the series that we claim. And this is where it gets weird. We're going to put a complex number here and here. Where this complex number is, I want to call it the 3rd root of unity, but it's, this number, which if you square, you end up with, well, you already know, but it has the property that this sum is 0. If you want to, that might come in handy. It's this complex number. This sum is 0, and of course the whole reason we did it at all is that that's how you can factor something like this. It factors to be, I believe we settled on this, like that. So if you expand that, you're going to get, anyway, you get the idea. So these two identities are true. All right, so that's what we're looking at initially. I haven't done the decomposition yet, but oof, evidently we get a big decomposition. Okay, we get 3 powers of this guy, we get another 2 powers of this guy, and we get a single power of that guy. And then we've also got a plus z term, and then we've got the 2 weirdos with the complex numbers. And thank goodness that they're linear, right? It's just a single one of those. So 1 minus omega z, and then you've got another term, 1 minus omega squared z. Oof. So apparently, if you add all this up, the numerator will be 1. Yay. Now the rest of this is just kind of old trickery. It's like the same kind of stuff we just saw, or the same kind of stuff that you'd see in Calc 2. What is our denominator? It's all this stuff, right? It's like this times these 2 and this one. So if I multiply by the denominator, multiply by this gigantic denominator, what is the denominator? It's this, as well as one of these, as well as our 2 complex guys. Okay, there's our massive denominator. I'm going to multiply that by this whole fraction, and evidently that cancels to give me 1. So we get a statement like 1 equals, and then this times the first term should give me a times, and I get a bunch of other stuff. So I get a times, looks like all 3 cancel, so you're left with just the 1 plus z and the 1 minus omega z and the 1 minus omega square z. Oh boy. And then in the middle, that one, unfortunately, only 2 cancel, so you do get an extra 1 minus z sitting there. But other than that, it looks just like this. I think I'm going to write them all out. I'm not going to try and like get clever and combine anything. Partly because I'm lazy, but partly because like, so this time only one of them cancels and you're left with 2 of these factors. But partly because when in a minute we're going to plug in just a number like z equals 1, and it's easier to see that it cancels if I leave the linear factor, right? What else? I guess that's the only thing there. So one of them cancels of the cubic that was there, and you do get the other annoying terms. Squared z. Oof, okay. And we got a bunch more. What a nightmare. Oh well. Oh well. All right, so denominator times this guy. The 1 plus z cancels, but the other ones survive. So you get 1 minus z cubed, 1 minus omega z, 1 minus omega square z. E, this one cancels, but the other stuff stays. So it's e times a cubic times 1 plus z and 1 minus omega square z. And then finally f. That last guy is the only one that cancels. You're left with this stuff out front. Yeah, I know. Sorry, this one's boring. It figures that, like, I don't know. I guess I feel like, oh, it must be boring since I understand how to do this, right? Most days, I'm like, I try to do it and I stare at it for a half hour, and then the video ends. And then hopefully I figure it out later and I try to explain it in a review. But oh, hey, thank you for the follow, Peepo. But yeah, today I kind of know what I'm doing. I remember partial fraction decomposition. So we'll see, though. We'll see if I actually know what I'm doing. You know what? Just so you can feel motivated if you're out there like, what on earth are we doing? The question was, how many solutions are there to this equation? X plus 2y plus 3z equals a fixed n. How many non-negative integer solutions to that equation? And it turns out the approach is generally to write out a couple geometric series, like the product of these 3 series. I started to write them out over here. But when you multiply those terms, it's a lot like summing up. It's a lot like what happens on the left-hand side, and your exponent becomes the right-hand side. Okay, that's hand-wavy explanation, but that's why we get this as the sort of first step. This is a generating function for the number of solutions of this equation. And so in this particular example, what we're doing is we're going to decompose that. We're going to take this answer and we're going to do a partial fraction decomposition. Why are you doing that? Because once you do that, like here we've got the decomposition. I guess here's a challenge, right? We're going to get from there to here. But anyway, he's doing this so that he knows what the coefficients are. Apparently this simplifies to end up being that, and now we're basically done. He took the magnitude of this answer, and he sees that it's like less than half, which means, sorry, he took the magnitude of this part, this chunk, ignoring the n plus 3 squared part. So he basically points out that in your coefficient, which is the exact answer, this term out front is it's less than 1 away, or sorry, the whole answer is less than 1 away from this quantity. So basically this quantity is the answer. The integer that is closest to this amount is the solution that you're looking for. So that's the upshot of this. I'm doing some boring part. I'm basically doing step 2. I'm basically confirming that these are the coefficients that you should get, and then I'm going to have to explain how we get from there to the series. but that shouldn't be too bad. First of all, this part's trivial. This 17 over 72 would just be, like, that's a geometric series right there. So that's just immediately zeta to the n. So one part of this series should be 17 over 72 times zeta to the n. So like that's getting absorbed right there. There is more, but that explains why the denominator is 72. If you square it, we would have to talk about like Taylor series to sort of explain how you get there. But if you take the derivative of this, you'll get that. And so that's probably where the alternating sign comes from. And if you take another derivative, I don't know, I'm getting a little sidetracked, but that's what's going to go on. That's how we're going to explain those two terms, is that they're basically just derivatives of a regular old geometric series. So they're going to get absorbed into, there's going to be a couple terms there. Right off the top of my head, I'm not sure. Oh, you know what? I think the n plus 3 is also coming from that term, but I'm going to have to see in a minute. I'm not sure. There's a negative term. Like this is 1 minus negative zeta. So if you just wrote a geometric series with a negative zeta, you'd get that. So that one is just that one. And then these two combine to be this weird trig term, which again, I need to see the details. I'm not sure that I'm going to flesh it completely out today. But you can see how it's possible. I will finish it. If I don't do it today, I'll do it tomorrow. But for now, at least, let's confirm these numbers, these coefficients in the decomposition. And then I'll try to sort of explain this. This is clearly a Taylor series thing, though, right? This power of n on top. I'm a little rusty. It's been like 10 or 15 years since or maybe a little longer. But yeah, this is a derivative of a regular. I already said all this stuff. These two are just derivatives of the basic form. So I think I feel like powers pop out, but I got to think about that again. Anyway, hopefully that makes some sense. That's why I'm spending so much time on this, or that's why I'm just verifying that this second line is true. And then I'm going to have to go back and review Taylor series so I can make sense of this line. But then finally, after all that, this coefficient is basically the number of solutions. That's what we've been trying to solve. His statement was that the answer is, there it is, can you see it? Is equal to the integer closest to n plus 3 squared over 12, which looks like madness, but it's coming right from that term, actually. Everything else is actually like less than half. So you're always one. In the solution here, in the coefficient, you're like less than an integer away from that. That's really the majority of the answer, is this form. But that comes from a Taylor series thing, and these numbers come from this expansion. And anyway, back to the easy part. Back to the easy part. Damn it. Well, this sucks. All right. Well, the good news is these were all like rational numbers, so nothing went too crazy. I don't think this was complex numbers. I think they actually work out to be like a ninth, I think was the E and the F. Should we do those ones first? If you let, let's do those ones first. If you let Z be, say, omega, that's going to kill off this term, because you're going to get 1 minus omega cubed, where, of course, omega is this madness. So omega cubed, I didn't write that down, I probably should. Omega cubed is, of course, 1. This is the cubed root of unity. So yeah, if we let zeta be omega, this becomes 0, and so everything that we had that has a 1 minus omega squared in it is, of course, 0. So at this particular value in our identity, I think it kills off everything except for f. Let's see, what about e? Yeah, it kills off this term too, right there. So all these guys had a 1 minus omega squared. They're all gone. If you plug this in, all you're going to get is 1 equals f times, and this guy, of course, does survive. What do we get here? Omega. Oof. We get 1 minus omega cubed. We get 1 plus omega. And then we get 1 minus omega squared. Yeah, that's it. 1 minus omega squared. I mean, one thing I can do, um, I mean, like this is negative omega. You can make use of this thing that I jotted down earlier. Like 1 minus omega, what is that? I mean, I'm just saying, like, what can we do with this? I could solve for omega, take 1 minus it, and see what we get. Maybe that's making it worse. Yeah, maybe we should just expand it and see what happens. I'm trying to see if there's like a clever way to just see what this number is, but another way that is a clever way is like you can use this identity as well. That was our factorization, but it doesn't always play nicely. Like if I plugged in 1 for z, I mean, up here, if I plugged in 1, of course we get this part, that's why I'm doing that, but we also get 1 minus omega, so these two could combine, and then you get 1 minus omega squared. Maybe that's nice, I don't know. Maybe we should do it that way. The alternative is to, of course, distribute this mess. Ugh, I really don't want to cube that. Or do I? No, I probably don't. Yeah, I'd like to avoid that, I guess. But the only reason I'm saying, like, oh, it might be fine, because omega cubed itself is 1. But, then I still got to do all this foiling, which I'm too lazy to do. So let's use this identity. If you let z be 1, you're going to see 3 on the left-hand side, and you're going to get this on the right. So that's probably something we can make use of. I can see we got one factor here. So we're getting 1 is f. I still got 2 more factors to play with. And I didn't take care of this yet. But one of those times this thing is apparently the number 3. And then, phooey. Like I know this is just negative omega squared. 1 plus omega is negative omega squared. Does that make my life easier? Maybe. Alright, well, you're going to have to foil something, buddy. Alright, this first chunk is 1 minus 2 omegas plus omega squared. You can put a 3 out front if you want. I'm looking at that. Sadly, this is not anything we saw before. I don't think. Yeah, I'm not seeing it. We could have also just done 3f. We could have just squared this, We could have done like this, the difference of 2 squares. I don't know if that's better. It is, right? It is better because... No, I'm not seeing it. Never mind. Yeah, never mind. Thought it was something clever, but I don't quite see it. Isn't it this? It's this with the 1 plugged in. This is 3. Okay. Great. Did we just use that trick a second ago? Why am I not seeing it anymore? Yeah, we just used that trick. Okay, good. Whoops. Okay, so rather than doing this craziness that I was about to do, I'm sure that'll work out also. Like, you just keep in mind that w cubed is 1, and you do some fidgeting with these identities. It would work out also. So evidently this is also 3. But yeah, let me slow down, make sure I didn't screw this up. We took one of these factors away, along with 1 minus omega squared, and I used this fact, because this is how z squared plus z plus 1 factors. That's actually where this came from, these 2 denominators, is that they factor like that. So that chunk is 3, that gets rid of one of them. And then, why'd you say that? Well, because I left one of them, but 1 minus omega times 1 plus omega is that difference of 2 squares. Right? Yeah, it is. The omegas and the minus omegas cancel, and you're getting that. So good, that's another 3. So we're finally getting 1 equals 9f after my long toil. And hey, do you remember that was supposed to be a 9th? I don't know if you remember. I'm excited, but I'm excited that it's a 9th, baby. I think we just did f, so it's supposed to be 1/9, and it is. I'm sure e is the same. you just let z be omega squared. Maybe it's kind of boring. This is the part of the paper where the person would say, you know, by a similar computation. Anyway, if you take omega squared and you throw it in all this mess, oh my god, what happens? This term becomes 1 minus omega cubed, and we've said it a couple times, omega cubed is 1. So anything with this factor is going to become 0. That's this guy, and this guy, and this guy. It's all of them except for the e term. That's the only one that did not have. What are you doing? Oh, no, that's right, sorry. All of them but this guy. This guy has just a single linear, you know, 1 minus omega z term. So when you multiply everything by this denominator, that's the one guy where that cancels. And so if you plug in z equals omega squared, that's the one guy in this big mess right here. That's the one guy that survives. So we get 1 equals e times 1 minus z cubed. In this case, z is, oh my goodness, 1 plus z is omega squared. Yeah, I don't know. I apologize. I know this is lots of just number crunching. It's kind of boring at this point. But if you were around like 10 minutes ago, I explained why on earth we're doing this. We were trying to solve the number of solutions to this equation, x plus 2y plus 3z equals n. We're trying to find the number of natural number solutions, like positive integer x, y, z. And it's a medium length story, but if you take the product of these geometric series, the coefficient that you get for the nth coefficient would be the answer. So what we're going to do is take this product, and I don't know if you've had Calc 2 before, but you do a lot of these where you do partial fraction decomposition on stuff that looks exactly like that. And that's what we're doing. It's a little longer than usual because we got 6 terms, but hey Lexi. Hey Lexi Timey. Good to see you. So omega squared, it's going to be almost the exact same computation. What am I missing here? It's a cubed, it's a plus. This one's not there because it canceled, but this one is 1 minus omega squared times your number. So that's omega to the 4th, but of course omega to the 4th is omega because omega cubed is 1. So that's just omega right there. Huh. Well, this is a little gross. I can see that this is negative omega from one of our identities. So I'll probably do that. But I don't see the other ones. But it must be this again. You keep using this trick, right? If I took one of these powers times 1 minus w, that's going to give you 3. So we already know the answer is a 9th, so I don't know why I'm so surprised, right? But this in the middle is still there. I don't think I did anything with it yet. Oh, I was going to say this is negative. We'll do that in the next step. This is, of course, let's just do one of them right now. This one's, of course, 1 minus omega. Oh, yeah? Did you do some partial fraction stuff in systems? That's cool. Did they do a lot of series in systems theory? I'm not familiar with it. I'm only like a... Anyway, you definitely did this in calculus too, when you talk about like power series. Well, usually it's presented like you do it as part of integrals. It's like, oh, I want to integrate this product of crazy things. And so that's usually the motivation for... Dave's getting ink everywhere. I got some... This has become an art stream. Yeah, usually the motivation for this is like, you want to integrate 1 over x minus 2 times 1 over x plus 3. That's how they usually motivate it in Calc 2. But partial fraction stuff comes up now and then. You know, so then you could split this into something like, can you still see this? Yeah. It's just, this is going to be logarithms. This is going to be 2 logarithms. But you need to find the numbers. Blah. This is a 3. evidently, because of this identity that we had earlier. Checking my poor little nib. It's still fine. I don't know, my nib. Man, oh yeah, we said this is going to be negative omega because of this identity. I guess that's the easiest thing to do with it. So I've got 1 equals 3e times 2 of these and a negative omega. This is clearly 3. But I don't see why. This is some obvious arithmetic trick that I'm not seeing at factors, right? Here's one of them. There it is. This is no, like it must factor like this. So you've got this, and I'm claiming that this is 1 minus omega. But let's prove it, I guess. If you distribute this, you get negative omega, and then you get plus omega cubed, which is a 1, right? So this chunk right here, you get negative omega, and then you also get plus omega cubed. So you're getting this. So that's why this is 1 minus omega, and that's why this product is going to be 3 again. So we end up with 1 equals 9e, which is what we were hoping for. Here, Lexi, this is the answer to the question. This is a good review. 20 minutes ago I went over this. The question was, this is the answer to the ultimate question, but what is the question? The question was 25. Find the number of non-negative solutions of x plus 2y plus 3z equals n for a fixed n. So his answer to that is like, well, it's the integer closest to n plus 3 squared over 12, which seems to come out of nowhere. But then his answer is to look at the series, do a partial fraction decomposition on it, and then this is going to take some more Calc 2 explaining, but this stuff, just like 1 over 1 minus z is the sum of z to the n, you could also express this as a power series. And if you do that, this coefficient will be your answer. So that's the quick explanation for why we're doing all this stuff. So just in the past like 20 minutes, I've verified these two. I spent the first 45 minutes like reviewing partial fractions and convincing myself that this factors like that. Anyway, but in the past like 10 or 20 minutes, we got the 2/9. So I verified those numbers. And I want to verify the other ones too. We got like 4 more to go. But this part's all kind of easy. This is just algebra. This is not the hard part, really. Although, what is the hard part? The hard part is that I couldn't have done this on my own, right? I would definitely need the solution to figure it out. Let me pause for a sec. Alright, let's finish up our partial fractions. I'm going to leave this mess on the screen. Ooh. So motivational. Never mind this splotchy confusion. Oops. Never mind this. This has nothing to do with anything. Okay. We got E and F because I was excited about those complex numbers. But we still got to do the other ones. I don't know. Let's do like A. If you want to... Wait a minute. Is A a good one? Yeah, A is a good one because A is an easy one because if you let Z be 1, everyone else has a factor. I guess I wrote it here. Everyone else has 1 minus Z as a factor. 1 minus Z squared, 1 minus Z, 1 minus Z, 1 minus Z. Where is it? 1 minus Z. So anyway, it's the only one that doesn't have 1 minus Z as a factor. So if we had let Z equal 1, it'll kill off everything except the A term. you'll get 1 equals A. And I think we said Z is 1, so you're getting a 2. I mean, should we do it slowly? I don't know. 1 plus 1, 1 minus omega times 1, and 1 minus omega squared. But I think we know this 1 minus omega times 1 minus omega squared business is 3. So this is a 3, and that's a 2. So we're getting 6A. A is a sixth. So B and C are going to suck. They're not going to be quite as easy because I can't just plug in. Unfortunately, like they both have a factor of 1 minus Z on like the A case. So I'm not sure what I'm going to do about them. D is going to be easy though. If you just let Z be negative 1, we'll get 1 equals, we said Z is negative 1, so this dies, everything dies except for the D, and you get 1 minus negative 1 cubed, 1 minus, I guess that's really a plus, right? And 1 minus omega squared times negative 1, and that's it. Again, this is 1 plus omega. Damn, that's not the same as what we used to have. That's okay though. And this one's what, 2? 1, yeah, it's 2 cubed. Interesting. So 1 is 8 times some junk. Clearly this should be obvious, but I don't see it off the top of my head. So this is like negative omega squared, and this one's like negative omega. Is that going to be enough to make this really easy? Yeah, it is. Omega cubed is 1. So this junk is 1. So we're getting 8D. So D is 1/8. Alright, now to the annoying parts. What the hell am I going to do with B and C? Those are going to be some nasty fractions, man. Well, I mean, so if you plug in 0, I guess we're just going to have to get a system of equations. We're going to get two equations, right, in B and C. Yeah, I don't know why I'm doing this. I could just trust him. I did this like maybe 18 months ago. I did something similar to like confirm that he got the right numbers and stuff, but anyway, part of the I decided to start streaming this because like at least then I'm somewhat accountable. Like if I tell you guys I'm going to be on 2 or 3 times a week, then I really should do it, right? So it's helping me actually progress through the book, even though that's kind of an absurd task. I've brought this up a couple times, but there's like 750 problems in this book. And the real way that you use a book like this, because it's not a textbook really, it's just problems. Oh, I guess I lied. Look at this. He's defining an integral. That's good of him. Looks like he's defining a Riemann sum. He's telling you this is what it would mean to be Riemann integrable. Anyway, so yeah, integrals as sums of rectangles. That's about the only explanation, that's the only exposition in the book. Then he just jumps into problems. Here's 1, here's 2, here's 3. So mainly the book is just a big series of problems, but the awesome thing is he has answers. Like the last half of the book is all solutions to all these problems. Some of them are super short. So it's kind of cool, like the last sentence of a lot of answers, he'll pack a lot into like one sentence. So then I spend like an hour trying to figure out what he's saying or like why it's true. But usually if he doesn't explain, it's something obvious. Like usually once I get it, I'm like, oh, okay, yeah, that's why he didn't say anything, because it's like, it is doable. If you're familiar with it, it's easy, but if you're not, you might still have questions, I guess. That's also part of the reason I'm trying to stream this, is like, if anyone else looks at this, sometimes you hit a snag and you're like, how did he get that? Like, why is that true? Even in this one, even just in this one, like the next part that's going to be hard is like, this part's easy, what I'm confirming now. Getting from here to there, if you don't already know about Taylor series, like you sort of have to have done Calc 2, or like there to there makes no sense at all. Even if you have had Calc 2, figuring out why this is that, it takes a minute to confirm. The eighth is clear, and this part of that is clear, but the other ones, that's something to do with Taylor's theorem, and this one's like a trig thing, obviously because of the cosine, but I mean, yeah, this one I don't remember off the top of my head. It's going to have to do with our omega thing, our cubed root of unity thing. If you add these two together, apparently you get that. I don't know it off the top of my head, but I'm pretty sure that's true. That makes sense. But we'll have to verify it. I don't know why, but we should. Yeah, it's definitely messy. We were working on B and C. Those are the ones that are missing. Everything else we actually have, the other four numbers. So what I would usually do, I usually don't deal with ones this big, but what I would usually do is plug in z equals 0. It's going to give us some nice numbers. You could literally just grab any integers you want at this point. Like we could do 0 and 2, and it'll... The only thing I'm nervous about is that, like, we got these omegas in here. We have some factors that for every term we get like a complex number. So 0 is nice. 0 is awesome. It's going to kill off those complex numbers. But anything that's non-zero, I don't know where we're going from here. But anyway, some sort of fiddling and we'll get two equations, and that should, B and C should pop out. Should not be that complicated. So if I plug in 0 into this big mess, we get, well, we don't get 0 for any of them. It's not like any of them die off. What we get is a times some stuff. It might just be a, actually, right? 0, 0, 0. So we just get a plus b, yep, plus c. Those are all ones. So a and b and c and d and e and f, right? D and E times 1 times 1 times 1. Yep, you just get the whole sum, of course. But we know these numbers. I mean, so this was really just a statement about B and C. We already know the rest of the numbers. A is a sixth. D is an eighth. E and F were each 1/9. So we know that B plus C is 1 minus these fractions. So we could figure that out. What I'm going to wish we had was like another one, a distinct, another equation in B and C. Well, okay. If you look at B and C, they only differ in that C has an extra factor of 1 minus z. Can I take advantage of that? I don't see how. And you don't have to do it this way. What I was saying before is just take another integer. Take like 2. We did 1, -1, we did 0. You could take anything. You could take a fraction. You could take 1 over omega if you want. Somehow I don't think omega or negative omega or anything like that is going to help us. Oof. Yeah, that just gives me a lot of... But then again, is 2 going to help us? Right? 2 doesn't play nicely with omega. That's not a great idea. Well, Dave's trailing off, isn't he? So close, man. You're so close to just crunching this number. Let me waste some time. Gee, what's this? 8 plus 6. 8 plus 6 over 8 times 6. Alright, we may as well do that part, I guess. Plus 2/9. Is 14 out of 48? I believe that. Is this a multiple of 9? I don't know. 46. That doesn't sound right. 27, 36, 45. Oh, okay. So no, it's not a multiple of 9. Are you kidding me? Okay, fine. If I triple it, it'll be a multiple of 9. If I triple it, what do you get? 120. 136 maybe? It doesn't feel like a multiple of 9. It's not. Did I do this wrong? Is 3 times 8 16? Of course not. Okay, good. You did it wrong. Good. Okay, 3 times 48 is 120 plus 24. There you go. Something like 144 is what I meant to say. Is that a multiple of 9? I mean, yes, but like, you sure about that? It's 12 times 12, so yeah. All right, sure. So we triple this, we get blink, blink, blink. We triple this, we get 30 plus 12. And then this one, I'm just going to cheat. What's 144 over 9? 16. Multiply this by 16. 16 over 16. So 2/9 is the same as 32 1/44, evidently. Okay, so this mess is 1 minus 74 over 144. Or in other words, the sum of B and C is, what's this, 70? 70 over 144? Something like that? Yeah, sure. Why not? Yeah, sure. All right, well, now what? Back to the hard part. What are you gonna do? Oh my god. So another tack would be to expand everything, which is not what we're gonna do. But that's one thing you could do if this was like a Calc 2 problem. You typically, in fact, that's what I did earlier when I was reviewing like an hour ago. We did omega and omega squared. I'm almost tempted to just try like negative omega, right? Because I know that sounds painful, but it's probably not as painful as putting a 2 in here. I don't really want to deal with like 2 omega and 2 omega squared and stuff. I'd almost rather have everything deal with omegas, because we have some formulas that work with that. Should I try it with 2 and see how bad it gets? Because here you'll get nice numbers, like that's a nice number, but here it's not. 1 minus 2 omega times 1 minus 2 omega squared. I just don't know how I'm going to deal with stuff like that. Let me jot something down real quick. If I had like 1 minus 2 omega times 1 minus 2 omega squared, what can I even do with that? Plus 4. It's 4 omega cubed. So we still have this junk. Oh, maybe it's not as bad as I think. Because this is, we know what that is, I believe. It's negative 1. Okay. Maybe I will go with 2. Because this equals 0. This is negative 1. So this number is this. It's this. It's 5 plus 2. Yeah. This is 7. Wow. Okay. Maybe we will do 2. You see why I was paranoid though, right? And some of them it's not going to be quite that nice. These ones, it is that nice. But the E and the F, they're not going to be quite as nice. But maybe we'll see what happens. Maybe we see what happens with this z equals 2 case. All right, sir. 1 equals. Then plug in 2 for all these friggin' numbers, man. You get a 3. 1 plus z. 1z is 2. Oof. You get a 1 minus 2 omega. Come back to that one. 1 minus 2 omega squared. We just talked about that, though. That's going to be 7. I'm about to see a bunch of those, so we'll probably write that as 7, okay? Is that it? That is it. And then for b, you get 1 minus 2. I don't know why I didn't just write it as negative 1. 1 plus 2 And then you get the two things that we just said was 7. Indeed. And then you get c times 1 minus 2 squared, 1 plus 2. And you get the 2 that we said was 7. And you get d times 1 minus 2. Can we just make this negative 1? 1 minus 2 cubed. This product, which we claim is 7. And then you get some stuff that I can't just hand wave the complex part, sadly. So we get e, but we know those e and f, we know those are ninths, so that's not as bad. Negative 1 cubed, that's a 3. This annoying thing is 2 omega squared. And then you get an f times negative 1 cubed, that's a 3. And that's a 1 minus 2 omega. Yikes. This is a 7, of course. So 7 by 3 is 21. Negative 1 times 3. So this is 21 with a negative. Interesting. That's a negative 1, but it's squared, so that's gone. That's a 3, and that's a 7. So this is 21. It's still there. That's negative 1 cubed, still there. So we got negative 7d. That one's cubed, it's still there. Yep. Ish. What am I going to do with that? Well, I guess we'll see in a minute. We do know e and f, of course. It's supposed to be 1/9, but I'll plug those in a minute. I don't know, man. I don't know. All right, minus 3, 1 minus 2 omega squareds times e, and then minus 3 times the other one. Oh, well, and these are both ninth. E and f are the same number. So at least these combine. The two omega guys are going to combine. What is it? Minus 3, 1 minus 2 omega times f. So because like there's a 3, there's a ninth, everything's the same except for those two terms. So they do get grouped together. It might not be as bad as I thought. What on earth is wrong with you, Dave? Why are we doing this? Do you ever stop in the middle of a computation and be like, why am I doing this? No, we must forge on. No, you don't do that. Ours is not to question why. It's just to crunch the numbers. So 21/6. I don't know B and C. But look at that, we do get a difference of B and C, which is kind of what I was after. If you want, we could write it as, what would be easier? Let's just do a plus, I guess. Plus 21 times C minus B. Is that okay? Because I don't know B and C, but the rest of the numbers I do know. D is 1/8, I think we said, so 7/8. E and F we know are 1/9. So this stuff at the end, you got 3/9, 3/9, and then there's this junk in the middle. I'll take it slow. A third, or 3/9. You get 1/3 of this, and you get 1/3 of this. Yeah, right. So we can shuffle these over there. We got a C minus B. And now this is the only stuff we don't know, but we can, I don't know. What is this? 1/3 times this sum plus 1 minus 2 omega. 2 minus, oh, look at that. The 2's factor. The 2's factor, baby. Sorry, see the two ones? They combine to be 2. I'm factoring the 2 out, and I get 1 minus omega squared minus omega. Hey, why does this look almost good? It's not quite good. What is it? I know that this is 0. Clearly this is something nice. It's 0? Is it 0? I don't know. This is -1. So, oh, it's 2. It's 1 minus this. And that is -1. Right? This junk is -1. So I'm looking at 1 minus -1. So there's an extra 2 there. So all together now, hey, we did it. It was pretty bad, but it wasn't as bad as I thought it was going to be. I thought it was going to be like impossible with lots of weird decimals and stuff. Minus 7/8, and then this is the junk I'm dealing with now. It's actually minus 4/3 because I'm claiming this is a 2. 1 minus this thing that works out to be -1. I knew that looked familiar. Yeah, so if you had a sum, omega plus omega squared, this sum is 0, which is why I'm saying this is -1. This is -1. 1 minus -1. So you're looking at minus 4/3 right there. So a little more fraction, a little more faction crunching. Fraction. If you add these fractions, you'll get another equation. And dog's going crazy. We're not going to have room for that. So I'm just going to say b plus c equals 70 over, yep, that was right, 70 over 144. And now we're going to have like a c minus b or whatever, b minus c, something like that. Wow, we are somehow getting near the end. 1 plus 7/8 plus 4/3 minus 21/6. Divide all that junk by 21, and you will have yourself a formula for c minus b. Come on, brain, you can do this. 16/24 is a multiple of 6, so let's triple this. Okay, let's triple it. Did you get that right? And then this times 8 is like, come on, brain, you can do it. What is 8 times 4? 32? That seems like a power of 2. And then this is 4 times this would be 84. Alright, those are my fractions. They still equal 21 times mystery number. So c minus b is equal to, we'll get something in a minute. Oh my goodness, 53. Well, you could also do this. So 24 plus all these things. Like that. And then we'll divide by 21. Well, let's not do that. Let's actually do it here. 45, 87, right? 87, 45, 75, 77. 77, bro. All right, 77 minus 84 is like 7. Is it -7? Let me just make sure I'm not going crazy here. It's not that hard to do, but it's also easy to go crazy. Yeah, -7. Yeah, of course it is. Still over 24. That doesn't go away, but we divide by 21 and we'll get, eesh, what a gross number. 24 times 21. 504? Kidding me right now? Well, anyway, we have finally solved for b and c effectively. If I add these, you'll get 2c. This is insanity. I mean, you could at least have this. Okay, is this divisible by 7? Ah, okay. Good. This is 1 over 72. And the other one is what? 35 over... Yeah, no, it doesn't. You can do this, brain. But all I'm getting is like 35 over 72. I guess that is what it is. Can't do more than that, right? No, this is not a multiple of... Not a multiple of 7. 7 and 5 and... Nope. 7 and 5 and 6 and 12. It just isn't quite happening. These are primes. So, alright, never mind. Cool. So what were you going to say? Well, if you add these, you get 2c. If you add these, you get a formula for 2c, which is 34 over 72, which means c is you know, half of that, 15, 16, 17. This is C. After all that work, just to confirm, this is C, A, B, C, 17 out of 72. All right, we didn't screw it up. And we're supposed to get a quarter for the other one. If you subtract these two, if you took this minus that, the C's would cancel. If you took this minus that, you would get 2B. So if you took 35 minus this, which would be adding 1, so it's 36 out of 72, which is half. So you're getting B is half of a half. It worked. Well, we have confirmed that Pólya is not crazy. I'm sure he verified this 100 years ago, but we verified it again here today, that this is how you decompose this crazy fraction. All right, so we got the numbers. What does that have to do with anything? Why are we doing that? Well, okay, this crazy series is this series. It decomposes like this with the numbers that we have found. Maybe I should write them down somewhere. We got E and F, we got A is a sixth, we got B is a quarter, we got C is 17 out of 72. That's a cute one. We got D is 1/8, so that's all of them. Hold on to that. But now we go back into calculus land. In fact, maybe this is a good place to write it. Man, this is a long video. Yeah, indeed. I should have, yeah. Should have said that at the beginning. Damn it. Why didn't I think of that? So I got to do some quick review here, because I don't remember how this is going to work out. This is, of course, true. But if you differentiate this, so this is this series. Everyone knows that. But if I take the derivative of this function, the constant goes away. You get almost the same series, but there's a power, right? So if I take the derivative of this, actually it looks like you just get this back, right? Like I'm saying, if you had fz is this, and you use the power rule and the chain rule, you pull the -1 down, you get the -2, and then also you multiply by the derivative of the inside. So the two negatives actually cancel, and you do get this as the derivative. So this is the derivative, and when you differentiate term by term inside here, you get kz to the k minus 1. That's like how you get 1, but here you get 2z. You don't just get z back. And then next you're going to get 3z squared. You don't just get z squared. So it is changing the coefficients. The 0th term is gone. It's okay to just ignore that and start at 1. But I think we should maybe re-index this so that the powers are z to the k again. We should maybe insist on starting at 0. That's just a thought I had. So there's the derivative. That's how you would have a formula for this type of fraction. Oh, you know, this guy right there. If you wanted to write that as a series, you would have to write it like that. And then if you differentiate again, I guess I never did it, but if you differentiate here, you get, there actually is no negative, because the two negatives cancel from the chain rule and from the power. But if you do it again, a 2 pops out this time, but it's -2 times -1, and so a 2 pops out, and you get yada yada. So we do have a 2 that we have to deal with, but other than that, it's a very similar conversation to what we just had. We could deal with this if you want. We're going to do the same trick where I re-index, but let's differentiate this one. It doesn't matter. You could do this one too, and then you're going to be shifting twice, but who cares? So let's do this one, I guess. Again, I think we're going to say I'm going to ignore the first term, because when we wrote these out, we got, when you plug in 0, of course, you do get a 1 from the derivative of that guy. But then you get like 2z and 3z squared and 4z cubed, etc. So anyway, that's the thing we're differentiating. So yeah, this number, this fixed number is still there, but you differentiate this, you get kz to the k minus 1, and that's kind of why I may as well start at 1, because when you differentiate this, you get 0, so you're not actually going to even see it. If you plug in 0 for these, also, the formula is consistent. It gives you k equals 0, so there's nothing there. But when I do plug in k equals 1, I think we get something. We get the constant. We get 2. We get 2. If we plug in 1, we do get a term, and that term is 2z. Wait a minute. No, it's 2. It's the number 2, excuse me. Yeah, 2. And then after that, you get 3 times 2, and 4 times 3, and 5 times 4, etc. Just 2 factors, right? It's like the powers keep coming down. It's sort of like a factorial action happening. Yada yada. So again, I think we should probably reindex this so that it both starts at 0 and our power is the actual power and not this weird. So this is the same series as starting at 0 and looking at k plus 2 times k plus 1 z to the k. I believe that's the formula you're going to get for this. There's an extra 2 there, but other than that, pretty nice formula. Okay, so that was all I mean about Taylor's theorem, Taylor's formula, which we didn't even need, actually. We didn't even use it. We just used if you know what a geometric series is and you believe me that you can differentiate term by term. So I guess technically we used we took the limit. We believe that you can swap this order, you know what I'm saying? Same as the sum of the limit of yada yada. So if we believe that you can bring a limit inside of another limit, you can exchange the order of the limits. If you believe that, then you believe you can differentiate term by term and yada yada. So yeah, I needed these 2 formulas. Do we want this? Maybe we should multiply that out. I'm just trying to think ahead here, so the next step is as nice as possible. I'm noticing that this case, okay, if you just had this, it's half of, we start at 0, and you get this times z to the k. I'm just noticing that this is true. And of course we're going to want this. We're going to want this also. This is the case for the square. I think we are, yeah, we're like almost done with this problem. It only took me an hour of review and an hour of tackling. But it will help me, because number 27, I don't know if 1 or 2 of you was here back when I was babbling about it, but like this problem that I've been working on, I'll say it, I'll just mention it again. This problem that I've been working on is this one, right? And you do a partial fraction decomposition, like we said. But number 27, so this is 25, where he says 1x and 2y and 3z equals n. In 27, he just picks numbers. He takes numbers that are relatively prime, but he takes L different numbers, and then he starts talking about this equation. And he has this observation about the solution. And so I think we really want to get 25 down, because his answer for 27 is basically just going to be an application of 25. He's like, well, a decomposition into partial fractions, just like 25, is going to give you this. And so like what we're about to see that happens, it comes up again in 27, just more generally. Like the coefficient that you see is going to be pretty much the same pattern that you see in 27. So I'm going to hold on to this junk. But what were we looking at? We started with, we had this, we said it's this. So now I want to say, all right, this series is a power series. I know this one. That one's easy. It's just c times a regular old geometric series. And this one's easy too, because it's 1 minus z. So let's forget about the numbers for the moment and just say, like, what would this be as a power series? How would you write these fractions as a power series? The first one we just addressed. But I'll rewrite it. A over 1 minus z cubed, b over 1 minus z squared, c over just a regular 1 minus z. The only one I'm happy with, frankly. The only nicely behaving one. Anyway, d over 1 plus z. And then the two weirdos, e over our complex dude, and f over his mate. That's omega squared z right there. Yeah, so now what I'm doing is saying, well, this equals something times z to the n. What is it? And yeah, it's going to be massive, and it's going to involve a, b, c, d, and f, but, you know. But it clearly can be done, because these are all just linear, and these ones are the two derivatives we just looked at. So those ones can also be done. There's just a little coefficient up front. So let's jot it down in terms of all these letters, and then we're almost done. The first one we just said is a times this. So I'm going to get a over 2. Should we skip the sum? There's going to be a sum in all of these things. Starts at 0, goes to infinity. We'll skip the sum because they all have the sum. So a over 2, and then this term. I don't know. K squared plus k plus 1, I think it said. No, you screwed that up. K squared plus 3k plus 2 is what it was. But that's okay, we'll come back to that. The b term, it's b, and then it's just a k plus 1. Yeah, I don't quite see. Oh, you know what? I bet this factors. I bet when you, like, if I just plugged in the numbers for a and b, these numbers combine, right? Like the 3k combines with the bk. Well, I guess it's really like a over 2, 3k. Anyway, I'm betting this is going to factor to be like basically the answer. Anyway, I'm getting ahead of myself. There's a c, and that one's just c times, you just put a 1 there because it's a geometric series. It's this one. There's just a 1 here. So if you got a c on top, then you got a c there. So it's just a c. The d is a little more interesting. Just to make this very clear to everyone, this is also just a geometric series. It's just that easy. So this time we have a negative 1 to the k is how you're going to handle 1 plus z downstairs. That's a pretty common trick. So that's what's going on with d, is we'll have d times negative 1 to the k. And then you got, Dave loses steam. What do we do with this one? The other ones were just z, like I handled that one with the derivative. Isn't it just, oh, okay, it's just, yeah, it's the same trick. It's the same trick. This is the power, you know? This is, this is the base of the thing that you're, so we're getting omega to the k, z to the k. Yeah. Hey, it was a tough problem. You want to know how many solutions to this x plus 2y plus 3z equals n are, don't you? That's right. You go back to work. You do those 6 partial fractions. So I was saying this is what we're looking at. We've got an e on top, just e times this. So it's really just this. I'm going to write that for now, but we're probably going to need it. We're going to need to think about like what a formula for this is. Our omega is, of course, the cubed root of unity. Sexy stuff. It's modular, right? It's periodic. Like every 3 of these, it just kind of collapses on itself. Yeah, what is... That's where that cosine term... Like, I'm remembering what he wrote. I can just show you. I'll just for the sake of pedagogy, this is what you're supposed to get. Something like a ninth, because the numbers were ninth. You're supposed to get cosine of 2 n pi over 3 is what I'm supposed to be getting for this formula. But I'm just trying to think of, well, of course you put the k up there, right? If you raise it to this power, yeah, this is safe. This is this. But that's, what happens to the sine term? I don't quite see it. I think he's acting like the sine term goes away. He got 2 pi. He has the same thing I just wrote down, but there's no imaginary term. You think he's just... Do you think he's just expressing this as 2 series, like a real and an imaginary part, and he's ignoring the imaginary part? That's a thought. It could be that simple. Cosine shows up with both. That's true. You're right. That is what it is. The cosine shows up with both. The sine also does, but I'll bet... Yeah, I'll bet the sine cancels, right? Now, of course, the sine would cancel if it was just one term. So it must happen every time. I just didn't see it yet. Yeah, you're right. I think it's like, so it's going to be like 2 cosine this is how it simplifies. Yeah, thanks for the tip, Stucky. So yeah, it's not like what I just said. He didn't ignore anything. It's more like when you add up omega and omega squared, you get -1. Yeah, I mean, you get the real part. You don't get the imaginary part. So this is true that it's this, but we don't want to stop there, is what Stucky is telling me. You should probably continue, add these two together and see what you get. In fact, we can do that because E and F are the same, of course. They're both 1/9. So it's pretty much legitimate to say, I mean, just for the sake of, nah, I'm going to wait. I'm going to hold off. I was going to write E with the omega stuff. Should we do that? Would that make people feel better? Let's do that. E omega to the k plus F omega to the 2k, I suppose. So it's all this junk times z to the k. We're kind of well on our way here. I bet if you plug in the numbers for a and b, you'll be able to factor this or make some sense of that, the k's there. You're getting like a second order polynomial in k. And then over here, this one I don't know clearly yet, but it's kind of what and stuff you just said, like the signs are going to cancel. Yeah, the imaginary parts cancel. So you're getting, this is not what I wanted to see. If we do this, we get Mr. Doop. So you get omega to the 2k, and 2k I didn't do, but you just get 4 pi over 3 k, you know. So when I add these together, if you add these two together, add these, okay, you'll get when you add these puppies, we're going to get, of course, this. But yeah, the claim is going to be that this is cos of probably 2 pi k over 3. Or maybe it's like two of that, I guess. 2 of that is what it's probably going to be, is my question. So, yeah, do you believe that? Here's the first term. here's the second term. I don't know if it's helping me to put a 4 pi there. I mean, do you even want to do that? No, I got to do something. So yeah, I kind of do want to do that. It's probably like, probably factor e to the 3 pi k and then like divide by 2 or something. 1 plus that. What I was imagining is if like you take the difference of these two and cut it in half, you could probably factor this to like center this around 0, and then the answer probably pops out. But what if I don't do that? I think we know. I was hoping it was easier to see just from this kind of. Like obviously if we add them, you get. The reason I'm hesitant is because like it depends on k, of course. You know, so of course we're getting like cos 2 pi k over 3 and cos 4 pi k over 3. And then we're also getting the imaginary parts. Sine 2 pi k over 3 plus sine 4 pi k over 3. And my hope was that like, oh, that just equals 0. Ta-da. It's certainly true for k equal to 1. I suppose if I want to be hand wavy, I mean it's not really hand wavy, but we know this thing repeats itself every like 4 terms, right? Every third term actually. So it's true for 0, it's true for 1. If I show it's true for 2, then we're done, right? By the time you hit 3, this thing has cycled back around. So when you look at cosine of 2 pi over 3, you're up here, you get negative half. I think we already addressed this. I said if you sum those two, you'll get negative 1. So when k is 1, here you get negative 1. And here you get 0. Is that believable? Because sine would be positive root 3 over 2. And over here, when k is 1, sine would be negative root 3 over 2. So it cancels. This equals 0 for k equals 0, 1. And if it's true for 2, then I'm claiming that we're done with that part of it. And we just get basically this. Wait a minute, why is it 2 cosine? This was just my guess. That's probably wrong. Well, the point is we could ignore that. We could just keep a cosine term there. But 2 of them, right? That's why it's 2. Yeah, I feel a little weird about that because there's a k. Well, stop worrying about it. So at 2 you'd get 4 pi over 3, which we've established is down here. And then 8 pi over 3. Confused. 8 pi over 3. Blank, blank, blank. Can I just like subtract 6 pi from this? 4 pi? What am I subtracting? Well, if you subtracted 2 pi, it would look like that. There you go. That's what you wanted to say. So this angle at 2 is the same as 2 pi over 3, which we just addressed. Okay, so it is true for k equal 2 as well. So actually that's a little hand wavy. I could have been a little more rigorous with that explanation, but you can see, of course, every multiple of 3 is going to give you the same, you know, this formula repeats itself every 3 terms. And I'm saying for 0, 1, and 2, for k, this imaginary part actually cancels out. When you sum them together, it just becomes 0. So there is no sine term. There are only cosine terms. I'm not gonna write down like a simpler formula for what it gets when you add them. Well, I guess I am, but I don't want to. I'm not gonna say it's like, oh, it's just -1. Um, but I guess I could, huh? Because at 0 you get 2, and at 1 you get. What do you get? So at 1 you get. We said -1, right? Yeah. Yes. K equals 0 gives you 2. K equals 1 gives you like -1. What does k equal 2 give you for this cosine business? It gives you 4 pi, again, we just had that. And it gives you 8 pi, which I said was 2 pi. So it should give you -1 again. Huh. Well, we can't actually use this information really because the k is still increasing and there's still like a dependence on this variable. So you could replace this coefficient with this piecewise thing, you know, that changes every 3 steps. But I don't think, anyway, that's not part of his answer, and it's a little bit maybe beside the point. I think the point's going to end up being like, oh, it's bounded by 2. It's going to be some simple observation. But what we have established is that there's no sign here. There's no sign function when you take this series out. So for this part, these two combined, careful, what are we going to say now? I think the observation was that this is just this, is what I wanted to write. So I'll write that for now. But we can combine that a little further, right? Like what is this one in terms of that? It's just a double angle. Well, so I was working on simplifying these, and the E and the F are both 1/9. So we got a 1/9. This first part gives you cos of 2 pi k over 3. And this other part gives you cos of 4 pi k over 3. And I think I already know, he's just going to say that's 2. He's going to say it's this. I only remember that because I saw it like 4 times, right? It's 2/9 of that term. Just think about that for a sec. Anyway, the numbers. You got numbers, man. You got numbers. Here they are. We took care of the 9ths. A over 2 is 1/12. You sure you want to write 1/12? Listen, man, I don't have a choice. We're going to figure out what's going on here in a sec. And then B is what? 1/4? Maybe I want to write it as 3/12 so I can combine these. Yeah, let's do that. Because I think these are going to combine. I sort of already know they're going to combine. That's like the bulk of the answer. C is this hideous 17 out of 72. And actually, that's all we write. Because C next, like, there was nothing next to C. There was no interesting. C was the one that corresponds to 1 over Z. So you just get 1Z to the K in your expansion. And then D has a negative sign in front of it. D is what, 1/8? Okay, so we get plus alternating with a 1/8 there. Probably could have written that a little nicer. Why is this 2 again? So 2 things are going to happen. We're basically done. I can finally shut the stream down in about 10 minutes. These are going to combine. We're going to probably be able to factor this. What is it? 3k plus 3. So we got k squared plus 3k plus 2. And then here you get an extra 3k plus 3. And so we'll figure out what that is. And then this is 2, but my brain is weak, and I just don't. it is of course symmetric, right? Why is it always 2? For some reason I thought it was like -1 some of the time, but oh, that's no. Why did I think that? Why is that wrong? So of course k equals 0, or 3, or 6, or 9, any multiple of 3, this is 2. But if you plug in like if I had cos 2 pi over 3 plus cos 4 pi over 3, isn't that -1? Here's 2 pi over 3, here's 4 pi over 3. I swear it's -1. Okay, fine, you'd be right. And the next one is going to be the other way around. It's the same number, actually. That's why I keep insisting that it's the same as this. This is the k equals 1 case, this is the k equals 2 case. But the k equals 0 case, you just get 1 plus 1. You know, any multiple of 3 case, you just get 2. So at k equals 1, I think you're getting -1 here. Huh. You know what? I'm thinking too much about this. He didn't say that you get 2. He didn't say that at all. He said you get this. He said you get 2 of cos 2 pi k over 3. He fully acknowledged that sometimes it could be negative. He didn't say he didn't replace it with a 2. He basically left it like this. So it's fine. I just need a, what is the half angle formula or double angle formula? Double angle formula. You like how I'm looking this up of all things? No, I don't want that. I don't want that. None of these are helping me. How about half then? I don't think that's gonna help me either. I was looking for. I just wanted to express this in terms of this one term, you know? But maybe I can just kind of observe that it happens. So I know this is -1. This part is equal to, it's not working. It's equal to this. And this part is the same story. Yeah, so I'm a little fishy on that. But it's this is a really easy. Well, stuck on a little really easy trig thing, I guess, but that's okay. This anyway combines to be k squared plus 6k plus 5, which it does factor, right? 5 times 1, but I just remember that he doesn't want us to do that. I think he wants us to complete the square. Okay? So you would have gotten 9, but there's a 5 there, so we'll subtract 4. Something like that. So these two combine to be these two combine to be 1/12 of this, k plus 3 squared over 12. And then for whatever reason, he just wanted to complete the square on k plus 3 in particular, because his answer involves k plus 3 squared. Otherwise, his answer would have involved k plus 5 times k plus 1, and I think it just doesn't look as elegant. It also does what? I guess tacking this extra -4 on, so here's part of it, that's still there. but that's this whole chunk right here. The first two terms are these two terms, same. And then there's also 17 over 22, or 72, excuse me. He's going to combine those. And then you got the alternating 1/8 business is still there. And then you've got evidently 2/9 cos of, I'm pretty sure it's the same as what I've been saying. It's 2 pi k over 3. You know? So yeah, these two fractions get combined. Like if you did 6 times this, you'd be able to you get a common denominator of 72, right? So 6 times 4 is 24, so you're looking at 17 minus 24 over 72, which I guess is -7, which is how that shows up, -7. So we're getting finally k plus 3 squared over 12, that's that number, minus 7 over 72, that's that number, plus the alternating over 8 is that number, and then this 2/9 of cos 2 pi k over 3, which I'm going to have to wave my hands on. But we're finally just about done with this. We've verified that this is the correct partial fraction decomposition and that this is what you would get. So we now know the coefficient out front. And then he just observes that, like, if you took the magnitude of this stuff, the stuff that you're subtracting, you know, the difference between your coefficient and this leading term, let's call this coefficient an. If you look at the magnitude of its difference between n plus 3 squared over 12, you'll get this stuff. And so he looks for a bound for that, and he notices that it's less than 1. Like, he just sees how big this number would be, and he says, well, really, this is the majority of your answer. It's off by less than half from this quantity. So whatever integer is closest to this quantity is the answer. So yeah, well, and the last thing would be, you know, take this coefficient we had, look at how big this part of it is, and you're getting, like, it's less than or equal to 7 over 72 plus 1/8 plus 2/9. I bet that's how he's getting this number. This is 9 over 72, and this one's, I guess, 14 over 72. So we're getting 16 and 14 is 30. Wait a minute, did I add that wrong? I'm getting 30 over 72, but I must have made a mistake. This is 8 times 9. This is, oh, I think I did 7 times 9. Wait a minute, that's not right. 9 times, yeah, I did 7 times 9. I meant 8 times 9 on this last guy. So I would have had a 16, I would have had a 32. That's right. Yep. Oh, you can't see what I did, but yeah. So that's what he's doing at the end there. He's explaining that we got this coefficient. It's some crazy integer, but if you cut off the front part of it, that quantity is less than half. So whatever this integer is, it's the one that's closest to, it's like less than half away from this amount. So this amount, you know, maybe the ceiling function or the floor function, whatever you want to use, but it's the integer nearest to this is what this number works out to be. Is the number of solutions to x plus 2y plus 3z equals n. Crazy, man. Well, I am going to log off, but I'll probably be back tomorrow, hopefully like around 1 or like 12:30, 1, something like that. I'll probably be back tomorrow. try and think about number 27 in the book. 27 is, it's like the third time I've said this, but it's basically the same question, but if we had relatively prime A's, what would be the number of solutions to this guy? A1 x1 plus A2 x2, yada yada, up to AL xl equals n. And he has an observation about the solution. I guess in our example, if we were to like, I mean, basically in our example, the AN worked out to be this quantity. So if we divided it by like n squared and took the limit, what would you get? Here we get, here we get what he says. We happen to get 1/12. Did he mean 2? Nope, yep, he means 2. Yep, okay. So if you take your answer and divide it by, like here we had 3 variables, L equals 3. But if you take this quantity that we got, n plus 3 squared over 12, and you divide it by n to the 2, and then take the limit, you're clearly getting 1/12 in today's example. And he's claiming that you'll always get 1 over the product of these numbers times L minus 1 factorial. So in our case, you're going to get, he's claiming that you should get this. This limit should be this, which is what we got. It's 1 over 4 times 3. It's 1 over 12. So ours is a special case of this thing. His answer, by the way, for this is like, well, just do a partial fraction decomposition, man. He's like, just do that, and you'll see that the leading term, the principal term, meaning like the majorant in this series, the guy out front that we just said was like less than half away from an integer. Anyway, the formula that you get for that should always satisfy that limit property. You know, if you divide by n to the L minus 1, take the limit, you'll get 1 over the product of these a's times L minus 1 factorial. And then hopefully I'll be able to figure this out too. But that's about all I've thought about. I don't know 27.1 or 27.2. Those are going to be bigger. So I'll probably be staring at them in confusion tomorrow. But at least 27 part 0, I was hoping to get a handle on by doing this stuff today. Starting to think maybe I won't have such a great handle on it. Because at least here we had numbers, you know. We had the numbers 1, 2, and 3. And the next example, he basically is like, what if you don't have numbers? What if you have so this is what we have in general for tomorrow's number 27, all the way up to AL. Let's like write that as an L. And so he factors them, and he's saying like, well, they're all going to have 1 minus zeta to the L. I mean, that when you do the partial fraction decomposition, this will be one of the terms for sure, because they all have 1 minus zeta as a factor. And there's other stuff. But yeah, there's a number here, right? You do this partial fraction decomposition, you usually call this A. If you multiply by the common denominator, you'd be able to plug in just zeta equals 1. So you would get an equation like 1 equals A times the rest of this stuff, like how all this stuff factors. So like 1 plus, oh, well, if you're plugging in 1, like this factor is like 1 minus zeta times, 1 plus zeta plus up to zeta, I want to say al minus 1, or is it actually just al? It should be minus 1. Yeah. So you have a factor similar to that for all of them. And when you plug 1 into that, you're getting al. You're getting al. Like for each of these. For this one, you're getting a2. So that's why you're getting this product. The factor there, besides the 1 minus zeta, is this geometric series that's finite, and it stops at 1 less than whatever your power is. So that's why you get this, and that's why immediately your coefficient in front of the principal term is this product. So that's also why he's not explaining much, because it's very clear, actually. I can finally turn a page. I got that part. Oh yeah, no, that's exactly what I got. He's describing, this is the biggest term. This is the first term in your decomposition. And since these are all relatively prime, the other terms are of lesser degree than this one. That's true. It's kind of obvious. It was clear in our last example too. And so the statement follows from the statement follows, period. He looks like he explains it in the future. But I don't think we need that explanation. We're going to have a similar thing, like this power. Like when you do when you go to write it as a series like this, in 27, the more general case, you're also going to have this n to the power of l minus 1 in the numerator, because this is an l, and when you do like l minus 1 derivatives, you end up here. If you take the derivative l minus 1 times from that geometric series, you'll get a formula like this. You'll get k plus, I suppose, l to the l minus 1. You'll be able to complete the square like that and get this kind of thing. In our case, we had 1, 2, 3, so this was 6, so a was a sixth. He's saying there's like an extra 2 there. Right. We got a sixth, and then we ended up doubling it. In this case, we ended up doubling it. Yeah, it's not actually double, it's factorial. It's factorial because when you take that derivative... my notes are over there. I see. I get it now. Right, this 12 showed up. There's a 12 there because there was a half in this formula. But the half came from derivatives. That's why it's a factorial. So if you take like L minus 1 derivatives, you're going to have L minus 1 factorial sitting there. So that's where the 12 came from. It's like this. All right, so 27 is kind of clear from what we just did. If you do L minus 1 derivatives of this series, you'll get 1 over L minus 1 factorial out front. Does that make sense? You'll get something like this, is what I'm saying. And then here you have basically k plus l and some smaller order terms, k plus l minus 1, etc. So, I don't know, maybe I'll be hand wavy next time on 27.0, because that part sort of makes sense. But then he has some observation about this volume. I talked about that last time. The only thing I didn't address was like, well, how come the number of solutions is in the derivative of this volume? So I'm going to see if I can make some sense of that before I tune in tomorrow. But then I haven't looked at 1 and 2, the next couple pages. I don't quite remember them. I might have looked at them like a couple of years ago, but I don't know them for sure. I don't know them off the top of my head, that's for sure. All right, lads and lasses. Thank you for watching. I must disappear. Have a great evening.